Hey everybody, Dr. Retzek here. This is our fourth video in section 6C. We have just broached the subject of orthogonal projection in the previous video, and now we'd like to gather up some properties of these projection maps. Let's get started. Okay, so let's remember where we were. The setting, it's our classic setting. We're in an inner product space here. So this box is called V. It's equipped with an inner product. We got a subspace in red here called U. And then its orthogonal complement, which is all the vectors in V orthogonal to literally everything in U, is called U perp. And if U is a finite dimensional subspace of V so that it's got a basis, then we may as well assume by Gram-Schmidt that that basis is orthonormal. So if you got an orthonormal basis in here for just the subspace U, then you can definitely write any V in the box as something from U plus something from U perp. So it's always possible to express V as U plus W, where U comes from the red and W comes from the green. So that means that V is the direct sum of U with U perp. And in fact, we even identified the piece of V that comes from the red. In this picture, you'll recall in the last video, little u was precisely V with E1 times E1 plus dot 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 V inner product EM times EM. That was the U in V equals U plus W. Okay, so that's where it all stands. What we want to do right now is just gather up a bunch of properties of the projection map. So let's remind ourselves how the projection map works. We defined capital P subscript U from V to V by when you do the projection to a typical U plus W, you just ignore the W. That's it. So you just lop it right off. The W doesn't matter. So take any input, any vector in V, express it as U plus W, and then lop off the W. That's how this projection works. Okay. Theorem 6.55 in the text looks daunting because I think it's parts like A through I maybe. We'll find out how long it is in a second. It looks like all this stuff, but any individual one of those pieces of the theorem is just a nice, straightforward fact that comes from the definition of the projection onto U. So let's gather up those facts. Let's talk through them. So this is theorem 6.55, and we could call this props of the projection. So the whole theorem goes with that picture that we're looking at right now. And it's just got a bunch of parts. Okay, first thing. Part A. This projection mapping, this is actually a linear operator on V. Certainly it maps V to V. We've already noted that. That's true by definition. The question is whether or not it's linear. And you guys know the definition of linear. Linear means it's got to respect addition, so that if you do P acting on V1 plus V2, that's the same as P of V1 plus P of V2. It's got to respect scalar multiplication, so P of lambda V is lambda P of V. So we have the definition of linear, and they're really easy to check. Like let's investigate the addition property. So this is a sketch of a proof. So at least as far as addition goes, say you got V1 and V2 that both belong to V. All right, then V1 is some U1 plus W1, and V2 is just some U2 plus W2. So each of those vectors is a unique red plus green in that picture. And remember, this piece right here, that is P acting on V1. And this is P acting on V2. So if you were interested in what happens when P acts on V1 plus V2, well, P acting on V1 plus V2 is nothing other than P acting on, all right, add V1 and V2. So what do you got? You got U1 plus U2 plus W1 plus W2. And this piece right here, that is P acting on V1 plus V2, and you can see that it equals P acting on V1 plus P acting on V2. So linearity holds. You guys can check scalar multiplication also. So let's just write maybe, how about we write scalar, let's do that in black. Scalar multiplication, similar, let's say. Scalar mult, similar. Okay, fine. So that's a proof of part A. So this really is a linear operator. Okay, fine. And now there's a bunch of stuff that's true. And it all follows from definition. So if you keep your wits about you, any individual one of these things is straightforward. Okay, here's part B. Check this out. If you start with something that's in the red already, well, think of that thing in the red as thing in the red plus 0, where 0 is in the green. And now you can see, oh, so I just ignore the part that's in the green. In other words, if you project something that's already in the subspace U into the subspace U, nothing happens. It's just U again. You're already there. Okay, cool. So that's true for all U that are already in big U in the first place. Sweet. Okay. Let's try another one. Well, we just figured out what happens when you do the projection to something that's already in U. What happens when you do the projection to something that's already in the green? Okay, so imagine you were going to do the projection of W, and you're thinking of W as belonging to the green blob. Okay, well, that's the projection. How do you think of this in the direct sum? If W is already in the green blob, then you think of it as 0 plus W. And again, when you project, you simply lop off the part that's in W, which leaves you with just the part that's not in W. So that's 0. And that's true for all W that already belong to U perp. Okay, cool. So look at those two, B and C. They say, if you do a projection to something already in the subspace, nothing happens. if you do a projection to something orthogonal to the subspace, you get 0. Cool. Okay. Well, we can certainly parlay those two facts. Let's think about the range of this operator. Now just think about this for a second. The range of the projection. You plug anything at all into this projection, the answer is the part that belongs to you. So certainly all answers belong to you. So the range is definitely a subset of you. But we just said, look at property B. We just wrote this down. If you're already in U, then you're definitely the projection of something, namely yourself. So that says any member of the subspace U is in the range. And that, in words, is subset both directions. The range of PU is U. Cool. Let's see. Well, anytime we talk about range, I guess we talk about null space also. I got another one here. How about, what's the null space of the projection? Okay, now keep your wits. When someone asks you for the null space of an operator, they're asking you for all the vectors that get sent to 0. Look at property C. Property C that we just wrote down says, well, certainly anything in U perp gets sent to 0. And if U got sent to 0, it's because the part of U that was in the subspace was 0. In other words, you must have been purely in the green blob in the first place. Anyway, the null space of the projection is U perp. Okay, cool. Let's go to F. All right, for any vector V, you write V as U plus W, where U belongs to the red. U is in the subspace big U, and W belongs to the green. W is a member of U perp. Okay, well, hang on a sec. Can we just subtract little u to the other side? So this implies V take away little u. Well, wait, what's little u? Little u is the piece that's in the red. Little u is V's projection into the subspace U. And that leaves you with just W on the other side. And where's W live? In U perp. So property F says if you take a vector V and you subtract its projection into U, then you are now holding in your hand something in U perp. Okay, cool. G, oh, this is a good one. G, I like this one. Okay, let's imagine doing the projection into the subspace U twice. Okay, so think about this for a sec. Start with a vector V, hit it with the projection. You now have an object in the red blob. Now hit it with a projection again. Well, wait, nothing happens. That's property B again. If you're already in the red blob and you do the projection, nothing happens. So if you project and then project again, no additional action takes place. So PU squared, doing the operator twice in a row, that's the same as just doing the operator once. So that's just a straightforward fact from the definition. Projecting over and over again, it's over after the first time. It's over. Everything's in U, and then nothing happens after that. Cool. Oh my gosh, how many of these are there? All right, here's H. H. Let's think about the sizes of inputs and outputs. So I want to think about how the norm of the output compares to the norm of the input, right? Do inputs get smaller after you do the projection, norm-wise? Or does the projection grow the size of vectors? And you can see, if you want to ask and answer that question, let's think about, for a typical V, let's look at the square of the norm of V. Well, V we know is written as U plus W uniquely. It's a direct sum after all. So V is U plus W. And in that expression, think about where U and W come from. U comes from the red blob, and W comes from the green blob. So they're orthogonal to one another. So by Pythagorean theorem, the square of the norm of U plus W is norm U squared plus norm W squared. And norms are bigger than or equal to 0. So this is bigger than or equal to the norm of U squared. Remember, ignore the W. That's how projection works. And so this object right here, at the far right end of this string of equalities and inequalities, this object, that is the projection of V. So I think what we just proved is this. If you take a vector V and project it, the norm of what you have in your hands now is no bigger than the norm of what you started with. The word for this is a contraction. Any operator that shrinks norms is called a contraction. So you could read property H as projections are always contractions. The converse is an interesting question, and you will be touching on that in some way on weekly homework 3. Is it true that if you're a contraction, you must be a projection? That may not be true, but maybe with some additional hypotheses. In any case, projections are definitely contractions. Okay, oh, there's one more, but the last one kind of brings us full circle. In fact, I'm going to scroll up way to the top of the discussion. Look back at the picture. When you endeavor to break a typical vector V into the part from U plus the part from U perp, you actually know the true nature of the piece from U. It's this. This comes from our proof of the direct sum statement. The piece that's in the red is that. That's how you find the piece that's in the red. And that's part I. So part I just says, recapping that statement, given ON basis for the subspace U, if you want to know the true identity of the projection acting on a vector V, well, that's the red part, and the red part is just V E1 times E1 plus ... V EM times EM. And that's true for any V in the big box. And that's it. That's theorem 6.55. Any individual piece of it is a really nice sort of classic use of definitions or earlier theorems or earlier parts of the theorem you're proving. They're all straightforward. make sure that A through I feel good and that you are ready to exploit these properties of projections to solve some problems that I think would be exceedingly difficult without linear algebra. Okay, I'll see you next time. Make sure your reading's good up through Theorem 6.55 for our discussion in class on Monday, and I'll talk to you soon. Bye.